Right, here we go. This program is about the unintended consequences of mathematics. The fact that mathematics written hundreds of years ago turns out to be suddenly something you need to explain quantum physics. Now that should be a real puzzle. People should be thinking, how can that be? Why would that possibly be? But because of the human condition, we don't stop and ask the obvious question. So let's dig into the program. And then as we go through it, hopefully you will realize that the universe is driven by mathematics and not driven by any fundamental forces. Gravity cannot be a force of any kind because you can't pull something with empty space. A magnetic field cannot be a force of any kind because one magnet can't move another magnet without touching it at all. So something's wrong. So the new definition of a force is the transmission of information which causes change. So let's see how well that fits with the program.
Hello, I'm interested in mathematics, wrote the Cambridge mathematician G.H. Hardy, only as a creative art. Hardy revered pure maths and scorned its application to the real world. In Great Mathematics, he wrote in the same book, published in 1941, there is a very high degree of unexpectedness. Yet what Hardy himself never expected was that in the decades since he wrote those words, pure mathematics would yield such an array of unintended consequences, not least through the wartime work of his Cambridge colleague Alan Turing, whose experiments with prime numbers led first to his crucial role in beating Hitler's codes and then to the birth of the computer. Yet Hardy shouldn't have been surprised. Pure maths was making itself useful long before the struggle against the Nazis. In 1801, centuries-old work on probability helped predict the path of an asteroid, then led on to the birth of population statistics, and the discovery of non-Euclidean geometry, meanwhile, was vital to Einstein's theory of relativity. To explore mathematics, how it generates all these unintended consequences, I'm joined by Colber Roney-Dougal, lecturer in pure mathematics at the University of St Andrews, John Barrow, Professor of Mathematical Sciences at the University of Cambridge and Professor of Geometry at Gresham College, London, and Marcus Giussotoi, Charles Simoni Professor for the Public Understanding of Science and Professor of Mathematics at the University of Oxford. Colber Roney-Dougal, can you start off by giving us an idea of the impact of these unintended consequences? Let's take cubic equations. The work on cubic equations, how did they lead 400 years later, rather dramatically, to the electric chair?
Okay, so we're going to start in 16th century Italy, and I'd better tell you what a cubic equation is. So a cubic equation is something like, I'm thinking of a number, I'm going to call it x, and I want so that x times x times x is the same thing as x plus 6. Now, I've picked that as an example because I can do it in my head and the answer there would be 2, but in general, these things are much harder to solve. Now, this had been a long-standing problem for thousands of years. People had known how to solve quadratic equations, x times x, but 16th century Italy, they finally discovered a formula for solving cubic equations, a bit like the quadratic formula that you might learn at school, but more complicated. Now, Girolamo Cardano published this formula and ran into difficulties. When he was trying to solve certain cubic equations, he knew that the answer was something straightforward like 4. But partway through his calculations, he was getting strange numbers, such as the square root of minus 121. Now, a positive number times a positive number is positive, and a negative number times a negative number is positive, so there's no such thing as the square root of minus 121. But he took a deep breath and said, well, let's just pretend that there is. And this was the birth of what's called complex numbers. If he pretended that there is, then when he finally finished his calculation, all of those funny numbers, the square roots of negative numbers, the complex numbers, cancelled out, and he was left with a perfectly valid number. Now let's jump forward to Victorian times and electricity. So the first kind of electricity which was widely in use is direct current, DC. That's the sort we get out of batteries now. And Thomas Edison was going around electrifying America and building power stations and connecting it to homes and factories, and people were bringing electricity in. There was a later kind of electricity discovered called alternating current, where the direction of the electricity changes direction all the time, hence the alternating. Now, the mathematics of alternating current is far more complicated because of this change of direction, but given Victorian technology, it was possible to transmit alternating current over far greater distances than direct current without wasting it through resistance. So Tesla and Westinghouse were strongly arguing that America ought to adopt alternating current, and so should the rest of the world. Edison was already wedded to direct current, he'd built a lot of the things, and so there came a period called the Current Wars, when Edison basically was running a PR campaign in favour of direct current and was trying to convince the world that alternating current was far more dangerous, which on some level it is. Now, Edison wasn't particularly pro the death penalty, but he so wanted to win these current wars that he got his employees to design, build, and later get the state of New York to operate the world's first electric chair running on alternating current to convince everybody it was dangerous. Now, ironically, the very same employee, Thomas Kennelly, who built the electric chair, 3 years later realised that this horrendous maths of alternating current could be massively simplified by the introduction of complex numbers to describe these waves and surges of electricity changing direction all the time. And so then the maths of alternating current became far simpler, and that's why when you plug something into the wall of a house today, it's alternating current that comes down the wire.
So
I'd just like to stop it there to talk about complex numbers, which is a mixture of real numbers and imaginary numbers. Now, in the mathematical universe, that should show up in reality. Well, classical physics is exactly that. The fields in classical physics are fields of empty space, or imaginary, because we can't see it and we can't feel it. So it's a parallel which has just not been recognized. The relationship between the Earth, which is real to us because we bounce off it, and its gravitational field or its magnetic field, which are both in imaginary land, that's a parallel that can't be ignored anymore as we switch over from physics not being able to explain physical forces, gravity, magnetic fields, and then suddenly just mathematics or information being the cause of things happening, the cause of action. A completely different way of thinking, but one that doesn't end up in contradiction.
400 centuries, he went back to those equations.
Yeah, I mean, they'd become school maths by that point. He was able to pull it off the shelf.
And do you think, just briefly, do you think this is what we're going to discuss is fairly common in mathematics, that unintended consequences follow time and again?
Yes, it is. And the further back we look, the more common it is, because in some sense, the bits of the early maths that we remember are the core of maths, and so they have applications.
John Barrow, why do you think this is? Is it something about us, a human instinct to spot patterns? Why do you think there's these equations pop up later to have such an impact?
Yeah, some people find it almost spooky that you can be challenged by some problem in the real world that you want to solve, or some observations in astronomy or physics that you want to explain, and you discover that a piece of mathematics devised apparently just for the amusement of pure mathematicians who thought it was rather pretty long ago turns out to be just what you need. My view of this is that it's not too surprising in one sense, because a good way of thinking about mathematics is that it's just the collection of all the possible patterns that there could be. It's a great catalogue of every possible pattern. Some of those patterns are interesting, some are not, some are useful, some are not. But sorry, it's an easy word to say, but what do you mean by patterns? Well, it could be patterns like we have on the carpet. There are symmetries. If you look at moving one step to the right on your carpet design or your wall design.
That's very strange. So he doesn't use the symmetries and patterns which are in nature because they're self-assembling. So snowflakes and snail shells and the golden ratio in sunflower seeds, they're all over nature. In fact, they define nature. And how could they be there unless nature was using the mathematics which makes the patterns? We really are stuck down a contradictory dead end.
If it looks the same every time you move one step to the right, or if you stand on your head and look at it and it still looks the same, you would say it's got a symmetry, it's got a pattern. There's something that you can do to it that leaves it unchanged. And our universe and the world around us has to contain patterns. We couldn't exist otherwise. There would be nothing for natural selection to act upon. So the world must contain patterns. So it's no mystery that what we call mathematics describes them. But what's mysterious is that...
Do we have pattern seekers because the universe is...
It's important to point out at this point that the patterns which appear in nature are not produced by any law of physics. So where on earth do they come from if they're not produced by mathematics?
Yes, so we have evolved within the universe in response to what the world is like around us, and it pays to be able to pick patterns and respond to them. And if you have a sensitivity for looking in the woods, as it were, in a rather vague way and sensing that something might be alive, then you have an advantage over someone who doesn't have that, because you could tell whether that something is perhaps contemplating having you for lunch, or you might be able to have it for lunch, or it might be a potential mate. So being able to pick patterns out certainly pays.
Can you give us an example of how pure maths finds these patterns and then they're picked up by scientists later? Just another almost like a complicated headline event. Let's take the astronomer Kepler and his reference to some ancient Greek geometry.
If you're an astronomer like Kepler was, you're interested in studying, in his case, the orbits of the planets in the solar system, or if, like Galileo, you're interested in firing cannonballs in the air and figuring out what the trajectory is followed before it comes back to Earth, then what you require to describe those paths in space are a group of curves that mathematicians call the conics, or the conic sections. And they were studied exhaustively and rather beautifully by Apollonius in about 250 BC. And Apollonius invented the names that we now use for them, the parabola, the hyperbola, or the ellipse. And if you have a body moving under the influence of a force like gravity, that falls off like the square of the distance the planet is away from the sun that's pulling it, then its trajectory will be to follow an ellipse if it's bound in orbit around the sun. If it's just flying past, it will follow a different trajectory, which is a hyperbola. If, like Galileo, we fire a heavy cannonball in the air and make a trace of its trajectory, then that will be following a parabola. So the geometry of these curves, which Apollonius...
So it's very important to point out this is not taught in schools. That in gravity, they're all following conic sections, as if you'd sliced a cone in different ways. Now that's very important. If it's that geometry, why not associate the geometry with gravity and not just teach gravity as an imaginary force? Very, very strange.
Studied by considering an ordinary cone, like an upside-down ice cream cone, and taking slices through it, vertically, horizontally, and then at an angle. And the shapes you get left on the surface of the sliced cone gives you either the hyperbola, the ellipse, or the parabola. And that's why they were called conic sections. They're sections or slices through a cone. And
did Kepler read about those? Did he know those?
Yes, this type of geometry.
So we're talking about 1600 years
1600,
later.
Yeah. So
1800 years later.
So at this period, the staple diet of mathematicians and astronomers like Kepler would have been the work of Euclid and then the work of Apollonius, which follows it. This was the basis for mathematical education.
Marcus Yusotoi, can you... I started with referring to G.H. Hardy and his disdain for applied mathematics or in any way. He wanted them to be kept pure. Can you just give us the distinction between pure mathematics and applied mathematics?
Yes, I would say that for me, an applied mathematician is somebody who's motivated by a problem in the real world that they're trying to unlock, solve, so that they can do a sort of a physical problem. A pure mathematician, which is, I would count myself among that camp, is one that isn't so much interested in the applications to the real world, but is celebrating the mathematics for its own beauty, and it's just motivated in some sense by a problem for its own sake. And I think that it's interesting, if you go right back to the Babylonians, for example, the Babylonians are solving sort of maths problems that look very practical. They're about measuring areas of fields and things like that, and that's where we get the quadratic equation, and they come up with, as Culver said, an equation essentially for a quadratic equation, how to solve it. But when you look at these problems on these tablets, these problems, although they sound very practical, an area of field is 60 units squared. One side is 5 units longer than the other. How long is the short side? you'd never know the area of a field without knowing the sides of the actual dimensions of the field. So this sort of problem is, although it sounds very practical, one of these scribes is actually doing it just for the pure love of undoing this little puzzle. And I think the motivation there has already gone, although it sounds practical, there's a mathematician is just enjoying the satisfaction of undoing one of these little quadratic equations.
Do you find that?
I do, absolutely. I mean, the wonderful thing is we're going to explore in this program is the unintended consequences. So although you will be motivated by the pure beauty of and the surprise, the thing that Hardy loved, that surprise of finding a new connection between things, time and again you find that those things, probably because they started with problems in the real world, then go into this wonderful abstract world of mathematics, but quite often they kind of land back down again as the thing that somebody needs.
What do you think draws you in? When I'll ask you, then go around. Draws mathematicians into exploring mathematics? Is it very much the same as poets wanting to keep right? Is it because Hardy made that analogy?
He did. He talked about poetry and that we're like a pattern searcher. I mean, John's already brought out this idea of pattern and structure, and I think we are drawn to similar structures that that creative artists are as well. But actually, I think it's interesting, this split between pure and applied mathematics actually happened quite late. And if you look, or still in revolutionary France, for example, revolutionary France was still very much motivated by practical applications. And when mathematicians in the academies were starting to explore mathematics just for its own sake, you get people complaining about this. Here's somebody complaining about the mathematician Cauchy in France, who was doing pure mathematics. He said, "It is the opinion of many people that instruction in pure mathematics is being carried too far at the école, and that such an uncalled for extravagance is prejudicial to the other branches." And so for revolutionary France, mathematics was empowering the state. It was used actually to do practical things. But then you get a change, and in Germany, there's sort of neo-humanist movement opens up with Humboldt, who's celebrating intellectual endeavour for its own sake.
Why was it so fruitful in Germany then to move there?
Well, I think what they really
in the
saw
19th
that,
century we're talking
yeah,
about,
we're talking 19th century, and I think they really saw that education, the universities should be taken out of sort of civil service and just celebrated for its own sake. And it really caused an explosion of celebrating mathematics for its own sake. And you suddenly get people the freedom to think about imaginary worlds that surely couldn't exist in our real world. And actually that allowed mathematics to breathe, which it didn't do in France. And you see a turn in the tide, because France used to be very dominant, and suddenly during the 19th century, 20th century, it's German mathematics which takes over. And here's Jacobi talking about pure mathematics and complaining about the French. He says, "The sole object of mathematics is the honour of the human spirit, and that, on this view, a problem in the theory of numbers is as worth as much as a problem of the system of the world."
So what you're saying is that in mathematics are the solutions to everything, really. That mathematics is the underpinning. It's back to the Galilei. I've discovered
it is the
book of the
underpinning.
universe. I've discovered the book of the universe. It's written in.
So there you've got him saying, is it the underpinning? Is it underpinning everything? Is it driving everything? And he used the word, these imaginary worlds. Well, a magnetic field is imaginary. An electric field, a gravitational field, imaginary worlds that we can't experience, purely mathematical structures.
The language of mathematics.
Yes, and it's
And you hold to that.
I do, and what I think we're going to explore in this program is how you have to free up pure mathematicians to think about things without consequences, to actually get the interesting consequences in the long run.
All right. Well, let's take a few examples for the rest of the program. Colvin, let's start with this chain of unintended consequences. Let's talk about the 16th century mathematician who was also a gambler. Tried to work out how to win all the time, and wrote a book about it. And then what?
So, Cardano, who's the man I just mentioned in terms of cubic equations as well, Girolamo Cardano, he's a mathematician, he's a doctor, and he's an extremely compulsive gambler, right, to the extent of having to pawn his wife's jewellery and go into the poorhouse at some point. He was the first person to calculate the probability of throwing a dice and getting a 6, of throwing 2 dices and getting 2 6s, and he wrote this book about games of chance in this very, very precise context, particularly of dice games. that was really the beginning of probability. Nobody had studied it until then. And there was little bits of nibbling away, mostly in the context of dice games. The next person I want to talk about is a Frenchman, Abraham de Moivre. We're now 17th century. He was a Protestant and so came over to England to avoid religious persecution in France, became friends with Newton. He started looking at this science of probabilities, was analysing, again, coin tossing, dice throwing, that kind of thing. And he was the first person, in some sense, to discover a curve which we now know as the normal curve or the bell curve. So that's the curve that you may have seen in various discussions of the human population. It looks the same if you reflect it down the middle. It's highest in the middle and it sort of slopes down gently to both sides, roughly in the shape of a bell. And he noticed that if you toss a coin repeatedly, say 10 times, the most common thing to occur would be 5 heads and 5 tails. That's the peak of my bell. And then as I get less and less symmetric, so 4 heads, 6 tails, or 6 heads, 4 tails, the probabilities slowly curve out the way.
So let's just show everybody, or tell everybody, where probabilities show up in nature. The whole of genetics, or Mendel's work on peas, is about probability. A 50-50 chance of being male or female, or a 1 in 4 chance of getting a red flower or a blue flower. But because we don't normally go from the biology department into the mathematics department, you don't connect those two up. You need somebody to tell you, think about genetics. Is it probabilistic or not? Is genetics part of the real world or not? Is it anything to do with human beings or not? Or is it already there? And you need the mathematics to drive it, because the fundamental forces don't do probability. Einstein hated it. God does not play dice. Well, who's doing the genetics? It's doing itself. So you can see how isolated we become when we go to university departments. That's the problem.
Now, having got this curve, he started thinking about other ways.
Just get to, for the listeners, don't we talking about? He picked up on Cardano's idea.
Yes.
So we have a direct connection here.
Yeah.
We started with the dice and now we're looking at probabilities. And can you just take us in the direction what he's heading this to Moivre?
Yes, so
what does he do with this knowledge? He works it, he advances it, and then what does he apply it to?
what he applies it to is pensions and annuities. So he's the first person to consider life expectancy. They'd just started collecting mortality data, and he's the first person to really consider the question of, if I take a 50-year-old man, how long is he likely to live? Until then, William of Orange had been paying out annuities at a rate of 14% a year, irrespective of how old the person was, and hence was losing a lot of money to some rich 20-year-olds who'd invested with him. And de Moivre was the first person to put on a scientific basis, how long is someone likely to live?
John Barrow, given that human beings had played games of chance for thousands of years before Cardano, why did this chain of discoveries only begin to happen with him?
It's rather mysterious. Arithmetic goes back to the beginning of recorded history, and algebra, geometry, almost to the, again, a similar ancient periods of time. But people, as you say, have been playing games of chance since recorded history. But the theory of probability is really very, very late. Why might that be? I can think of 2 reasons. One, you only got to look at stories like Jonah and the big fish in the Bible, where the seamen drew lots in order to decide what to do with Jonah and then cast him overboard. So it was a way of divining the will of the gods. So chance was the way the gods spoke to you. And so it's a rather risky business to start studying that. So that there might have been a turning away from a
risky
study.
In the sense that you're beating God at his game.
Yes, it's rather blasphemous. You're sort of inviting punishment. A more, but even so, you would think there are people who are willing to take that chance. The other problem, I think, is more practical. If you look at what was going on in the marketplace thousands of years ago, some dodgy individual would have some chicken bone which he would throw on the floor, and you would make a bet as to which piece of it was going to point towards you. Every chicken bone's different, and the fellow who owns it understands its biases, but there's no general theory of all the chicken bones. It's only when you have symmetrical die, like we're used to tossing, where there's an equal chance of any face coming down, that it makes sense to start having a theory about that. So I think this very simple idea of equally likely outcomes was what you need to really start developing a large arithmetic and mathematical theory of chance in the long run.
Marcus, can we take this story on a bit then? It goes from Cardano, to Demoivre, who, as Carl mentioned, became a friend of Newton's and, despite his great advances he made, died in poverty. And does that bring us, as the next stage in this particular story, because this is one of 2 or 3 stories we're going to tell, do we go to Gauss, to Germany, to Gauss after that?
Well, we can do. I mean,
would you like somebody?
Well, I would
go wherever you want.
Gauss is one of my favourite mathematicians. In a way, I suppose this is almost an unintended consequence for pure mathematics, you could say, because Gauss, I think, is probably the mathematician who encapsulates both the pure and applied in one mathematician. I mean, he was somebody who loved data. He became famous, actually, for rediscovering an asteroid that had been lost. They thought it was a new planet.
This is the late 18th, early 19th
Yeah, in fact, it was
yes.
found on the 1st of January 1801, the first day of the new century, and then they lost this planet behind the sun. They couldn't find it. And here's Gauss, the pattern searcher, who was able to take the data and rediscover a pattern in it and predict where it was going to be.
Again, just to keep us, we're still talking about something that kicked off with Cardano with the dice.
Well, yes, in some way, because it's about probabilities and errors of
so
data
and
where
on
things are
previous
going
work
to be.
is all I'm
Yeah, but
saying.
I was going to actually come to prime numbers, which are my favourite numbers, because here again is Gauss, who's great at understanding data. He takes lots of data about prime numbers, and he brings his intuition about probability actually to discover a pattern inside these numbers. These numbers don't seem to have any pattern to them at all, but by Gauss taking a sort of probabilistic view and saying, well, what is the probability that a number will be prime? And as he looks at the data, he realizes here is a pattern, and he's able to apply the probabilistic model to uncover something very deep about pure mathematics, which we now call the prime number theorem. So I think here's an interesting example of something which looks rather, probability does look very practical. And of course, it's very relevant to today's, we're all very bad at probability. That's why we need mathematics to help us through it, because our intuition is rubbish when it comes to probability. If you say 1 in a million people in London might have done this crime, well, there are 10 million people in London. That means 10 people would do it. For most people, 1 in a million means it's impossible. So the mathematics of probability has been incredibly important for us in our modern age in understanding risk. But I think the nice thing about Gauss is that he was able to go backwards and forwards between practical things trying to study an asteroid and pure things trying to understand the patterns in prime numbers. And even he would spend his time, I mean, I don't understand this as a pure mathematician, but he really enjoyed doing surveying of the German lands. I mean, he'd spend a lot of his time out measuring things. But of course, this leads also to an interesting bit of geometry, which I think John was going to mention.
I'll just explain the pattern which Gauss found in prime numbers. What he found is that there is an inversely proportional ratio between the scale and frequency of events. That is now known as Zipf's law, and it applies to earthquakes, collapses in the stock market, and even human ideas. So it was a very, very important thing to find. So really, this is the basis of chaotic systems which are not driven by classical physics. And all you can say is you don't know when the next earthquake will be, but there will be a pattern between the scale and the frequency of the earthquakes. That's all you can say. The opposite of classical physics.
Culver, to nail this asteroid first.
Sure.
1801 asteroid.
Yes, so, I mean, as Marcus said, it had been tracked for not very long by an Italian mathematician called Piazzi. He found it on the 1st of January. He got sick on the 11th of February, so there was a very, very small data set. Ironically, they were looking for it there because they thought they'd spotted a numerical pattern in the orbits as predicted by Kepler's laws of planetary orbits. So they had a good idea where they were looking. They found this object. They thought it was a small planet. There's a Hungarian astronomer who had taken the data from this Italian, published this very small data set and said, can anyone tell me where to look for this thing when it reappears
So this thing, which they
the
thought
sun?
was a planet, had disappeared.
Disappeared behind
and
the
they
sun.
wanted to know when it would come back and where
And
it would
where,
come and
yeah.
where. That was the.
You're going to lose it for a while
That's right.
behind the sun because
And
the
so
sun's quite big in
glare
the
of
sky.
the sun, and so it's going to then re-emerge when you'll be able to look again without being blinded by the sun. And the question is, where's it going to reappear? Where should you look?
So Zach published this data and basically challenged the mathematicians of Europe, including his young friend Gauss, to predict where the thing was going to reappear. And Gauss's prediction was way out of line with everybody else's. And he also said, this thing is not a planet, this thing is an asteroid. And it turned out that the 24-year-old Gauss was right on both counts. And what he'd done was he'd thought about this curve that de Moivre had found with the heads and tails. And he'd said, I think my errors of observation are going to follow the same shape. What's going to be most likely and what the average is going to be is no error at all. And what's going to become successively less and less likely is bigger and bigger errors. But an error in one direction is as likely as an error in the other. So by analysing the shape of the errors and seeing that that's the same as the heads and tails curve, he was able to predict where the asteroid was going to reappear.
John Barry, can you take us on to the next stage of this probability business here? We've got the asteroid, and then we're going into the revolution in statistics, aren't we here?
Yes. I mean, this ironically there's part of this story where you can see that a branch of mathematics is actually being created from the applications. So those early statisticians like de Moivre were interested in predicting life expectancy. They were part of the actuarial profession in a sense. But then social scientists started to think about systematically investigating trends of behaviour. You know, how many criminals do you expect there to be in 1 million people in a big city? How many people will die prematurely of TB? How many people will be disabled? And so forth. And it was argued that you could have a sort of what was called a social physics by Quetelet, Adolphe Quetelet, one of the pioneers of mathematical sociology and criminology. So he wanted to try and predict how the course of large numbers of people would develop in society. One of his great disciples was Florence Nightingale. She was one of the pioneering founding fellows of the Royal Statistical Society. And she was effective as a nurse, not simply because of applying tender, loving care and common sense, but analysing what was the result of moving beds further apart so infection wouldn't spread, and using statistics to evaluate the effectiveness of things in medical practice.
Colma, would you like to take that on a bit there? What Quetelet did? Adolphe Quetelet.
Yeah, I mean, so Quetelet was the first person to realise that, again, I'm coming back to this bell curve, our heads and tails curve, which then turned into our errors curve. He realised was applicable to just a huge range of human life. They discovered, for instance, that the chest circumferences of Scottish soldiers also followed this same curve. So there was a real astonishment at discovering that you could apply it to physical features of the human form and also to human behaviour. We've been talking about crime rates already. There was quite an uproar, coming back to John's earlier point about probability being trying to guess the mind of God. How could it be that crime rates were so constant when humans are endowed with free will? What were we saying about the propensity towards sin? But Quetelet really nailed it, basically. He was able to show that one has a certain probability of marrying at a particular age. That's not going to tell you anything about one individual, but it will certainly tell you about individuals en masse. And to start saying, we can look at how criminal justice systems, for instance, affect crime rates in a way which nowadays we're well aware of being discussed in the news all the time.
So do you want to add to that before we move on to to another example?
No, I'm happy to move on.
You're happy to move on.
It was controversial, as you had hinted at. In Russia, there were mathematicians who regarded statistics really as a threat to religious ideas of free will. And in Victorian England, there was strong opposition to statistics by people like Charles Dickens, who regarded as a great evil that this concept of the average man, the government could say, well, the lot of the average man is always getting better. And Dickens said, you just use this as an excuse not to do anything about the lot of the most underprivileged. So it was a controversial issue.
I want to move on a bit now. Can we go back to Gauss, back to Marcus's hero? The world for a long time believed that Euclid's geometry was the word of truth, like parallel lines never met, for instance, and so on. And his postulates held, and for goodness knows what, over 2,000 years. When that was challenged, what did that lead to?
you had to go back to the 1700s, beginning of 1800, and try to change your mindset a bit about how people thought about bits of mathematics like Euclid's geometry. Today we're used to thinking of it just as a tool that we use to figure out how to build the extension on our house or something. But for the medievals and later, it was part of the absolute truth of the universe. This is how things were. It wasn't.
Now that's very interesting to hear him say that people thought that mathematics was the absolute truth. It's how the universe was.
Yeah.
When Newton came along, we flipped over into physics and these fundamental forces, which are all a mystery because there's no physical contact between two magnets or any of the planets. If you'd have kept the mathematical idea, then no problem. But I think he's going to talk about general relativity and the fact that space is treated as a mathematical place and distorts, but it's not a physical thing. So you've got to keep those two ideas in your mind at the same time.
Just a description. And so the idea that this might not be the only geometry was something that was really resisted. It was almost anathema. And so at the beginning of the 1800s, and people started to think about whether you could have geometries which were not Euclid's. This is revolutionary in another sense. It's like a type of non-realism about the world. And you saw between beginning of about 1830 and 1832 several different people coming up with a rigorous way of describing how you would derive something like Pythagoras' theorem on a crumpled surface or a curved surface. So Gauss, again, we've just heard about, was one of the players here, claimed to have done it much earlier when he was younger, but Bolyai, a Hungarian, and Lobachevsky, a Russian, both involved in developing this type of description. And then one of Gauss's students, Bernard Riemann, really completed the story.
Well, I think this is a good example of the new humanist movement in Germany allowing you to think about sort of imaginary worlds. I mean, this I think what Bolyai called his geometry, because he just didn't think it had any application at all to the freedom to think about these other sorts of geometry which probably don't describe our physical world. It is what was important in bringing these alive.
Can we just elaborate first? We got this geometry of Euclid laid down. Parallel lines is a good example. Parallel lines will never meet, said Euclid, and everybody thought, although sailors knew that things weren't quite like that, but people went on believing it intellectually. So when they said, no, we won't, we'll take another course, and let's forget the risk, what did they find, and how did they find it? Can you just give us elementary?
Well, I think that, so the surface of the Earth is a good example. What is a straight line on the surface of the Earth? Well, you have to curve in order, you can't dig in through the Earth. And there you find there are no parallel lines, because if you take lines, the straight lines, the shortest path between 2 points are the lines of longitude, and you find that those meet at the poles. And so that was a geometry that Riemann discovered, said, okay, well, if you restrict yourself to being on a curved surface, you have no parallel lines. So here's a geometry which isn't one of Euclid's. And Bolyai and Lobachevsky and Gauss came up with others where there are many parallel lines through one point compared to another. So here were three different sorts of geometry, and then the question is, well, actually, which one is our universe? And that was what Gauss was doing when he was surveying Hanover. He was in.
So it's interesting to say the three different kinds of geometry, and which one applies to our universe. Well, under gravity, matter takes on positive curvature of spheres, but space takes on negative curvature, hyperbolic geometry. So gravity comes in positive and negative geometries, and that's not taught anywhere. But it's about time that we started to think.
She said, well, maybe light, when it travels, perhaps it does bend and somehow produce triangles with angles less than 180. Now, of course, surveying, he was putting lights up in Hanover, trying to look at the distances between things. But, of course, that was too small a scale to actually see the curvature of space. Now, the amazing thing is that these imaginary worlds, these imaginary geometries, are precisely the geometries that we need to understand the theory of relativity some 50 years later.
So that now brings us to Einstein, John Barrow.
Yes, Einstein always claimed that he wasn't a very good mathematician at all. He was a very good physicist, But he had a lot of help in his mathematics, fortunately for him. He had old college friends who were very strong pure mathematicians, and took a lot of advice and tutorials, in effect, on trying to learn about some of this very fancy and, to most physicists' minds, very abstruse pure mathematics that had come along in the 19th century. And until 1900, physicists wouldn't use anything more exotic other than Euclid's geometry, some calculus, and a bit of algebra. But Einstein had a conception of how the universe was fashioned, where he wanted to give up the idea that space was just like a flat Euclidean tabletop, and planets and stars moved around like balls rolling on this tabletop. That he wanted to give up this idea that space was fixed and unchanging. And his vision was that space was more like a rubber sheet, a sort of trampoline, and you dropped your planets and stars on it like heavy weights, and as they moved around they changed the curvature and the shape of the space as they moved. And in order to understand their motion, you just use this principle that Marcus mentioned, that things move so that they get from one point to another in the shortest possible time. And on a flat surface that means they go on a straight line. But on a curved surface, they don't. They follow the path that, the aircraft I'm travelling in from London to San Francisco follows over the surface of the Earth. But on a very wrinkled, wiggly surface, it's a more complicated path, like the one a mountain stream follows as it wiggles down from the mountain top down to ground level. So Einstein's picture of what gravity is and how it acts was bound up with curved geometry for space. That things move around, they change the curvature of space, and that curvature then tells them how to move.
So we have a direct line. Now let's take the last example, Marcus. We've got time for. We've got plenty of time to talk about it. Back to G.H. Hardy, his number theory. He was rather proud of the fact that it was pure and useless.
Absolutely. There's a mathematician's apology. I mean, it's a book I think a lot of mathematicians read when they were younger and brought up on, and it sort of instilled this ethos of celebrating mathematics for its own sake. And it's wonderful. He does celebrate number theory will never be useful for anything at all. And he says the real mathematics of the real mathematicians, the mathematics of Theorem and Euler and Gauss and Abel and Riemann is wholly useless, and he celebrates this. But at the end of the 20th
like
century,
Oscar Wilde, isn't it?
He's a character you love and hate because
no,
of this
not
kind
like
of
Oscar Wilde in himself. The phrase "all art is useless."
All right. Well, but the end of the 20th century, Hardy is proved to be completely wrong, because one of the things he was obsessed with was prime numbers, like Gauss. He was trying to understand sort of some structure in these primes. Riemann had come up with some ideas about the way the primes are distributed. And I certainly think he thought that primes were never going to be useful at all. They were a lovely plaything. Now, the same time as Hardy was around in Cambridge, you have Turing. Turing was somebody who, we all know perhaps because he cracked the Enigma machine during the Second World War. But what is unknown is that his ideas for using machines to crack codes actually was sparked by his interest in this thing called the Riemann hypothesis about primes. And he applied for a grant from the Royal Society to build this machine that would try and help to find how the primes were distributed. And he'd started to build this thing in his room made out of cogs.
Did they give him a grant?
They gave him a grant, I think, of about £60 or
Good
something.
for them.
But, yeah, and the blueprint still exists for this thing. It was never fully built because the Second World War broke out. Turing is then taken to Bletchley Park, where all of these codes are coming in. Again, this is like a little puzzle for him. So it's like a crossword puzzle. Here are all these codes. How do you undo them to see actually what the actual settings for the Enigma machine were at? And again, he thinks a machine is what should be useful for this. And he builds the bomb, which actually cracks these things.
The bomb?
The bomb is BOMBE is the name for... You can go and see this at Bletchley Park, actually. They've got a reconstruction of it.
Like the dessert.
Yes, yeah. But the idea, again, now of... originally, Turing's motivation was to try and understand prime numbers. He's able to crack these codes, shortens the war by 2 years as far as Winston Churchill is concerned. After the war, he comes back to this idea of a machine, and he realises the machines he was building were a bit useless because they could only do one thing, and he comes up with this idea of a universal machine, which is the forerunner of the computer. and suddenly he's going back, and he comes back to prime numbers, and the first thing that he tests on this computer is to try and beat the current record for the biggest prime number, which unfortunately his machine breaks down.
Hardy will be turning in his grave.
Not,
I mean, this
not
has been
only
useful.
that, but then we come to the internet cryptography, which is used on current day computers, which uses a beautiful theorem about prime numbers discovered by Fermat 350 years before the internet was ever thought of. And this beautiful little fact about prime numbers, which Hardy loved, we all love as pure mathematicians, is suddenly at the heart of the cryptography which is used by everyone when they send their credit cards across the internet. So this is the most amazing unintended consequence of pure mathematics than I can think of. I mean, okay, relativity is about describing the world, and probability, but this is number theory, prime numbers, creating the computers and the internet world that we use today.
Right. Culver.
Yes.
Do you want to interpolate an opinion or an observation on after that aria by Professor Dussault-Toy?
I wanted to come back to something which Turing had done, which was far more. So the stuff we've been talking about with the computers he was building sounds quite applied, but another of the ways in which Turing had got into computers was really thinking about the axioms of mathematics and the limits of mathematics, and he was interested in the question of, can there exist a machine to mechanically verify whether or not a statement is true or false? And as part of proving this, he invented, as Marcus mentioned, the universal machine. Now, the key difference with that, compared to previous computers, was that it stores its own program internally. The program is just the same as any other bit of data. This is what means that one machine can mimic any other, because you can feed in the program for any other. It's also, sadly, what's given us internet viruses. So we receive something that we think is a piece of data, just a word attachment, say, or some other attachment. What it's actually got is a program that your computer's going to run.
Pure mathematicians aren't responsible for viruses, so it must...
It's an unintended consequence.
Do you want to come in on this?
Yes, this idea of using prime numbers in this way, it goes back to Leibniz, Newton's great rival and adversary. So Leibniz had the idea of building a machine which was going to mechanically solve all human disputes because it performed logic. And the key about the prime numbers is another nice theorem of mathematics, that if you take any number, say 10, you can always split it up into a product of prime numbers, so 2 times 5, in one and only one way. And what this means is that if you take an ingredient of logic, a name or a concept, and you attribute it a prime number like 2, and then you have another concept and you attribute 5, if you combine them, then there's a unique result, 10. And so Leibniz hoped that by programming his machine with all sorts of political and religious statements, linking them to prime numbers, he could turn the handle and the machine would tell him whether the doctrine of predestination was correct, or whether liberals or Republicans were the correct party to run the country. It's horribly idealistic, but it was based upon recognizing that you can use prime numbers to uniquely characterize the way statements or concepts are joined together, and there's just one result.
And in some ways, this machine of Leibniz was a precursor to the enormous argument between Newton and Leibniz, which you covered not so long ago, as to who invented calculus, because Leibniz shows up in London with the prototype for his machine, goes to the Royal Society, promises to build them one, and never delivers.
Right. Thank you very much. We've got to get out now. Thank you both, Maroney Dougal, Marcus Dussault-Toy and John Barrow. Thank you very much indeed. Next.
Well, thanks for listening, everybody. That's another one we've done.